Simpson's rule is one of the numerical method which is used to evaluate the definite integral. Usually, to find the definite integral, we find the fundamental theorem of calculus where we have to apply the antiderivative techniques of integration. But sometimes it is difficult to find the antiderivative of an integral, like in the case of scientific experiments where the function has to be determined from the observed readings. Therefore, numerical methods are used to approximate the integral in such conditions. Other numerical methods used are trapezoidal rule, midpoint rule, left or right approximation using Riemann sums. Here, we are going to discuss Simpson's rule formula. Simpson's rules are more accurate than any other numerical approximation and are basically an extension of trapezoidal rule where the integrand is approximated by a second order polynomial instead of a first order polynomial. As you can see in the figure, Simpson's 1 by 3 rule uses parabolas to approximate each part of the curve. It divides the area into n equal segments of width h. So it can be proved that the total area under the curve by using the parabolic approximation is integral x naught xn f of x dx equal to h by 3 into f of x naught plus f of xn plus 4 times the odd terms, that is f of x1 plus f of x3 so on till f of xn minus 1 plus twice the even terms, that is f of x2 plus f of x4 so on till f of xn minus 2. Step-by-step procedure in order to integrate any function f of x in the interval a to b. The first step would be to divide the interval a to b into n number of subintervals of equal length, where n is an even number. The subintervals will be x0 to x1, x1 to x2 till xn minus 1 to xn. And the length or width of each subinterval is represented by h, where h equal to b minus a divided by n. Step 3 would be to calculate the values of x0 to xn as x0 equal to a, x1 equal to x0 plus h, so on till xn minus 1 equal to xn minus 2 plus h and xn equal to b. Consider that y equal to f of x. Now find the corresponding values of y, that is from y0 to yn, for the corresponding values of x, that is x0 to xn values. After finding all those values, prepare a table of the form as given in the slide. Then the approximate value of the integral can be found out by substituting all the above found values in the Simpson's rule. The main points to be noted down while using Simpson's rule is that make sure that the value of n, that is the number of subintervals, is an even number, and minimum of 3 points must be there for you to use Simpson's rule.
Now let's see a numerical example of Simpson's one-third rule. Here the question is to evaluate integral 0 to 6 1 by 1 plus x square dx. We know in Simpson's one-third rule there should be even number of intervals. So we divide it into 6 intervals, each of length 1. We get x values as 0, 1, 2, 3, 4, 5 and 6. We have f of x is equal to 1 by 1 plus x square, which is given in the question. So corresponding to each x value, we are finding out the f of x values, which is shown in the table. These values are represented by y0, y1, y2, y3, y4, y5 and y6. Now, according to the Simpson's one-third rule, the general equation is as follows. Integral a to b f of x dx is equal to h by 3 into y0 plus yn plus 4 into sum of odd ordinates plus 2 into sum of even ordinates, where h is the difference between the intervals, which is 1 in our case, and y0, y1, y2 are the f of x values. Coming to our question, we can write the equation as integral 0 to 6 1 by 1 plus x square dx is equal to 1 by 3 into y0 plus y6 plus 4 into y1 plus y3 plus y5 plus 2 into y2 plus y4. Substituting the values of y0, y1, y2 up to y6, we get the final answer as 1.36606. Now let's see a numerical example of Simpson's one-third rule. Here the question is to evaluate integral 0 to 6 1 by 1 plus x square dx. We know in Simpson's one-third rule there should be even number of intervals. So we divide it into 6 intervals each of length 1. We get x values as 0, 1, 2, 3, 4, 5 and 6. We have f of x is equal to 1 by 1 plus x square, which is given in the question. So corresponding to each x value, we are finding out the f of x values, which is shown in the table. These values are represented by y0, y1, y2, y3, y4, y5 and y6. Now, according to the Simpson's one-third rule, the general equation is as follows. Integral a to b f of x dx is equal to h by 3 into y0 plus yn plus 4 into sum of odd ordinates plus 2 into sum of even ordinates, where h is the difference between the intervals, which is 1 in our case, and y0, y1, y2 are the f of x values. Coming to our question, we can write the equation as integral 0 to 6 1 by 1 plus x square dx is equal to 1 by 3 into y0 plus y6 plus 4 into y1 plus y3 plus y5 plus 2 into y2 plus y4. Substituting the values of y0, y1, y2 up to y6, we get the final answer as 1.36606. Now let's see a numerical example of Simpson's one-third rule. Here the question is to evaluate integral 0 to 6 1 by 1 plus x square dx. We know in Simpson's one-third rule,
Algorithm. Now we'll discuss about the algorithm of Simpson's 1 by 3rd rule. First we start the program. Then we have to define the function. Now we input a, b and n, where a is the lower limit of integration, b is the upper limit of integration, and n is the number of subintervals. Then we have to calculate the step size, which is h, and h is calculated by the formula upper limit minus lower limit divided by number of subintervals, that is b minus a divided by number of subintervals. Now using for loop, by setting the value of I is equal to 0, store the value of x and f of x in an array, that is step 5 and 6. Now if I is less than n, that is number of subintervals, then we calculate x of I, that is lower limit plus I into h, and f of x. Now to calculate result, initialize result is equal to 0. If I is equal to 0 or I is equal to n, then result is equal to result plus f of xi. Else, if I mod 2 not equal to 0, that is when the number is odd number, then integration value is equal to integration value plus 4 into f of x. Otherwise, integration value is equal to integration value plus 2 into f of x. Since it is done by for loop, if the condition, that is I less than n, is true, step 8 and 9 is executed. The value of I get incremented and it will get repeated till the condition I less than n becomes false. That is when I greater than n, then steps 8 and 9 does not get executed. Now finally, Step number 11, calculate integration value is equal to integration value into step size, that is h divided by 3. Now we display the integration value, that is a final result, as required answer. Then we stop the program.
We have seen the algorithm for Simpson's one-third rule. So let's discuss about the C++ program to find the integral 0 to 6 1 by 1 plus x squared dx, which was solved numerically. First, header files are given, hash include iostream, hash include cmath. Using namespace std, function declaration is given. In this program, two user-defined function is used. They are float func float x and float simpsons underscore float ll float ul int n. Both functions are of float data type. Moving to the main program, int main, float lower limit, upper limit, int n. These are the variables. We have seen that is 6. C out, enter the lower limit. Enter the lower limit. C out, enter the lower limit. Enter the lower limit will be displayed on the output box while executing the program. C in lower limit. Input the value of lower limit, that is 0. C out, enter the upper limit. C in upper limit. In our question, the upper limit is 6. C out, enter the number of intervals. C in n, that is 6. C out, integration value equal to SIMPSON'S underscore lower limit, upper limit, and then function call is made. Since function call is made, float Simpsons underscore function will be executed. The variables ll, ul, n contains the value 0, 6 and 6. To calculate the value of h, that is step size, float h equal to ul minus ll by n. In our question, 6 minus 0 by 6, that is 1. Value 1 will be stored in the variable h. To store the value of x and f of x, array is used. Float x of 10, fx10. To calculate the value of x and f of x, for loop is used. For int I equal to 0, I less than equal to n, I plus plus. X of I equal to ll plus I into h. Fxi equal to func x of I. At first, the value of I is 0, condition is true. So, x of 0 equal to 0 plus 0 into 1. So, x of 0 contains the value 0. Fx0 equal to func x of 0. So, it calls the function float func float x. The variable x contains the value 0. It returns 1 by 1 plus x square. So, the value of fx0 will be 1. Similarly, x1, x2 up to x6 and fx1, fx2 up to fx6 will be calculated. When the condition gets false, it comes out of the loop. Since af- after Calculating the value of x and f of x. To calculate the result, sum of ordinates separately, we use for loop. At first, a variable res is set 0 initially. For int I equal to 0, I less than equal to n, I plus plus, if I equal to 0 or I equal to n. Relational operator is used to check the condition. Res equal to res plus fxi. If the value of I is 0 or 6 as in our question, it will execute the statement res equal to res plus fxi. Else, if I mod 2 not equal to 0, that is if I value is an odd number, statement res equal to res plus 4 into fxi will be executed. This statement is used to calculate the sum of odd ordinates. Else, res equal to res plus 2 into fxi to calculate the sum of even ordinates. Finally, the value of the sum of ordinates will be stored in the variable res. When the condition gets false, it will come out of the loop and the total value res equal to res into h by 3 is calculated. It returns the value to the main function and get displayed. So the output box will be enter the lower limit 0, enter the upper limit 6, enter the number of intervals 6, and the integration value equal to 1.36617. For the question, integral 0 to 6, 1 by 1 plus x square.
Let's have a look at another example. Here, the function to be integrated is log x. The program procedure is same as that of the previous one. Here, the only difference is for the function part. That is, the function to be integrated here is log x. The program execution begins with the header files and all the procedures mentioned in the previous one are carried out and the output is printed as follows. First of all, we have to enter the value of lower limit. Here we have entered the value of lower limit as 2. Then we have to enter the value of upper limit. Here it is 4. Then we have to enter the number of subintervals. Here the number of intervals is 4. Then the integration value is outputted as 2.15881.